thank you very much for the opportunity to talk to you today. I've really enjoyed and learned an awful lot. I'm full of questions from these other talks. I'm wondering what that bioplastic stuff tastes like.
Yeah.
I learned a lot when I was at Doc about science. One of maybe the most important things came from my friend and former lab partner Andrew, who's sitting in the audience here. I learned from him that what I thought was all the way off for a Bunsen burner was actually all the way on. That kind of helped me realize that maybe I'm not going to be one of those scientists in a lab with fire. So I ended up deciding computers were the way to go. So I'm going to tell you about a new way to learn about the universe. And now that I've seen all the other talks, I'm going to shamelessly rip off one of the great ideas from Robin's talk. Start there. So how do we learn what's beyond the solar system? Just in the big picture. Well, to get at that, here's a picture. All right, here's a picture of the Earth. It's a sphere. So to see the whole thing, you can unwrap it into a map like this. And there's lots of different ways to do it, and math nerds on the internet have great arguments about it. But we'll just say this is letting you see the whole picture. But what if instead of looking down at the Earth, you turn the camera around and look up, out into the universe? Well, you don't see much if you live near Los Angeles like I do, except all the city lights. But in an ideal world, you might see something like this. Okay. So you're mostly seeing stars here. This is the center of the galaxy. This is where a Sagittarius A star lives. Almost everything that you can see in this picture would be stars or nebulas or other things that we can see with visible light, mostly in our galaxy. But in different colors of light, the universe looks very different. Here's infrared. In infrared, you see a lot of dust. You see dust from stars formed long ago as this red stuff, and dust right here in the solar system, which is this blue stuff. In X-rays, which we just heard about from Robin, you can see lots of things, including matter getting so hot that it sends out these X-rays as it falls into a black hole. So you can't see the black holes, but you can see the matter falling into it. You can see some of the effects that has. If you could see microwaves, the universe looks kind of weird. You can see some stuff from the center of the galaxy, but other than that, green's sort of an arbitrary choice, but what we see is the same color, same brightness of light coming at us from all around us. It's nothing like what we're used to, where there's a little star here and a little star there. This is light left over from the beginning of the universe. It's called the cosmic microwave background. So the universe looks different in different kinds of light. But what I want to talk about is what about things that are invisible? What about things that you can't see with light, or maybe they're too dim, or maybe you can see the light but don't really understand it or what's creating it? If only we had another way to learn about the universe that's far away from us other than light. Well, it turns out that there's one other force besides electricity and magnetism, which light is made of, that can travel over great distances, and that's gravity. Einstein's theory of relativity tells us how to understand gravity. The gist of it is mass warps space and time. Matter tells space and time how to curve or warp, and space and time tell the matter how to move. So the sun warps the space in the solar system. It's hard to visualize warping of three spatial dimensions because you need a fourth dimension. There's some people on the internet that solve Rubik's cubes in fourth dimensions, but I don't get that. So the game we usually play is slide a piece of paper through the middle, and that's 2 dimensions, and then show the curvature in the third dimension like this. So imagine a big heavy ball of sheep. The planets try to move in a straight line, but because the space is curved, the straightest possible line they can move it is a circle. Now, like Robin mentioned, gravity works the same outside a black hole at the same distance of the same mass as outside a star at the same distance and the same mass. So what actually makes a black hole is that gravity is so strong that it has this thing called a horizon. The horizon is the surface. That's the place where, if we're outside the horizon, gravity feels the same to us as the same distance from a star. But let's say we take my twin brother Jason down there, and for science, we send him down into the black hole. He can send us some messages on it from his ship. He can send us radio waves until he crosses through this sphere called the horizon. Once he's in there, he's not coming back. And not only that, tell us anything about what's happening. And not only that, there's a singularity inside there where gravity is strong enough that it's not going to be good for his health. So, sorry about that, brother. So these are dead stars. They're formed from ordinary stars when they run out of nuclear fuel. Nothing can hold them up anymore, so they collapse into black holes. If you took the sun and squished it down so small that if it were centered right here where we're sitting, it wouldn't even reach to Philadelphia, you would have a black hole. They're incredibly small and dense, like Robin was telling us about earlier. But their gravity looks very similar. So if you take a piece of paper, slide it through here, and show the curvature, well, now the horizon is just a circle cutting through this plane, but the gravity is the same exact shape as the gravity of the sun. It's just as long as you stay out here, it's fine, but if you go down inside the horizon, that's where it's trouble. Now, if you put two of these together, something really interesting happens. Here are those two black holes' throats, just like I was showing you one of them. And when they spiral together and merge, they send out these ripples. These are ripples of gravity, ripples of curved space and time. These ripples travel at the speed of light, but they're not made of light. They're made of gravity. One thing really cool, well, one way to picture them is, imagine going out to the pond out here, taking a stick and stirring the stick in the water. You're sending little ripples outwards. And if you were really clever and had a great measurement of those ripples, you could figure out, well, how is the stick spinning and stuff like that. That's the game we want to play. Black holes are invisible, but by picking up these ripples, we want to be able to figure out what they were doing when they crashed into each other. Another great thing about gravitational waves is, unlike matter, everything's transparent. So these walls are opaque. Light can't get through it. Light can't get through the center of the galaxy, invisible light. But everything is transparent to gravitational waves. So what do? Imagine we have a super loud wave coming straight through us into the stream. And imagine this was a circle where all the particles are the same distance from the center. Here's what a gravitational wave does. It stretches and squeezes space around you. So you would get taller this way and squished this way, and then vice versa. This is showing that effect that they're moving by 10% of their initial height. That wouldn't be too fun if that were happening to you. That's uncomfortable. But this is way more than what the loudest gravitational waves we can get on Earth do. The loudest waves we actually get do the same effect, except instead of 10%, it's 0.00, however many zeros this is, 1%. If you were to build this and put one of the masses 2.5 miles this way at the end of a vacuum tube, that's what this is. Another one 2.5 miles that way, that's like this one right here. How much motion is this really? For the loudest waves we can get, it's 1/10 the size of a proton. I'm part of a collaboration called LIGO, where thousands of scientists and engineers have figured out how to make the detectors work and then make sense of what these detectors see. And the way they work is by using lasers to make the most precise length measurement we've ever made before. It's a whole other talk how this works. What I want to tell you is just some of the things we've seen. So, one day before 1 month after I got married, we saw the first gravitational wave. So I want to show you what this diagram means. So there are two curves here. We'll get to what the curves mean in a second. The pink one comes from one of our detectors. These are those big, long vacuum tubes I showed you a picture of in Washington State on a nuclear waste site. Here's one. The green one with all the trees was in a swamp in Louisiana. That's the blue curve right here. So blue curve is Livingston, Louisiana. The red curve is Washington. I don't know how those sites were picked, but I think Congress was involved, so... Now, I'm showing you a graph of time. So you can think of this time going by kind of the same way. It's like, if you're watching a TV show and the hero's like been hurt and he's really not doing well and they're showing his pulse going by on this thing or something. Or if you've ever seen a seismograph, this plays way better in California when I mention this. You see a seismograph measuring earthquakes. Time's going along like this. And I'm only showing you 1/5 of a second, so this is about the time it takes you to blink once. What I'm showing vertically is for each detector how much they were getting stretched and squeezed, the way I was showing you. But I had to scale it up. To make it go from -1 to 1, I had to multiply the fractional squeezing and stretching by this obnoxious number here. Because it's such a small effect. Even with our exquisite detectors, right here, it's just noise. Like they don't agree with each other, you're just seeing noise. But now, right around local disturbance, but it's something that came from outside the solar system. And in fact, I cheated a little bit and lined them up. We can actually tell, because the waves move at the speed of light, we can tell they came from one detector first and the other one 7 thousandths of a second later because of the time it took the waves to go from one to the other across the country. Yeah, when I was flying here from California, that sounded pretty good. Now, when I first heard about this, first I thought it was a test. And when I found out it was real, the first thing I did was kick all my students off the computer. My brother can identify with that feeling, I'm afraid. And I started running some calculations. But I let the students back on. We all started running calculations to try to see if we could model this with two black holes crashing into each other. And the result is this yellow curve. So back here where you're seeing noise, they don't agree, but you don't expect them to. But here where you see the wave, they track each other really well. This is just a rough cut of an idea of how you can use these computer calculations to interpret what you sense with this new sense humans have, to use gravity to look at the universe. So that calculation had two black holes in it doing this. They're spiraling around each other and merging into a big black hole. This is showing you what it would look like up close in 100 times slow motion. You wouldn't want to be there, but if you had a camera there, you would see the gravity is so strong that it bends the background starlight with this weird little pattern, this wibbly wobbly pattern here. And I should also say this movie and the calculations are done mostly by two of my students at Cal State Fullerton. Nick is doing a physics Ph.D. at MIT. Varun here is an electrical engineer. So I'm way down on the list from Wall Street, but I'm one of the generic employees of electrical engineers. I had great fun working with Varun. We didn't give him too much of a hard time about not being a physicist, being an engineer. Okay, from the waves, you can interpret, by looking at the waves carefully, what the black holes were like. By checking the spacing of these peaks here, we can tell that this black hole was 31 times the mass of the sun, and this one was 39 times the mass of the sun. The computer calculation I just showed you reveals that they reached a quarter of the speed of light, stars way more massive than the sun, moving near the speed of light. Then they formed this potato-shaped black hole here, and then it settled down to a new big black hole, 67 times the mass of the sun. Now, if you look at these numbers here, 31 plus 39, they don't quite add up. The Limerick generating station takes a couple pounds of mass and destroys it every year and turns it into energy. In a fraction of a second, this took 3 suns worth of mass and converted it all into energy. This is by far the most powerful explosion we've ever observed, and yet it's invisible. We can only sense it because of this new sense of gravitational waves. We've seen lots of black holes since then. This is a movie where oh, I didn't know there was sound. Okay. Okay, thanks. So, this is showing the different black holes. There's 2 here, but one's too small for you to see, and they merge to create these different kinds of black holes. These are their horizons, and these are the waves they make. By looking at the waves, they're like fingerprints that tell us what the black holes were like. And there's one last thing that we saw. Most of these waves were about a blink or a few blinks. But then, last August, we saw one that stayed in the detector for minutes at a time. Well, a minute and a half, maybe. And by the way it interacted with our detectors, we could tell people with telescopes, hey, maybe you should look over in this region. So they looked at this galaxy. This is Hubble before all this. And then there's this brand new thing you might never have noticed otherwise. This is the debris from 2 neutron stars, which are like atomic nuclei but the size of a city, and they smashed into each other near the speed of light. And we can tell that and how that kind of crazy nuclear matter behaves from looking at these waves and then looking at the light that comes from them. And the last thing I want to tell you about is that this is not work that you have to wait to be a professor to do. I hire students in their first year of college. Most of the work, much of the work I was showing you was done, it's done by teams of thousands of scientists, but also that includes a lot of undergraduate students. Almost all the students in here are undergraduates, and we have a few master's students. So if you find yourself heading to college anytime soon, don't just take classes. Research in college is not reading about what other people did and writing a paper. Sorry for the English department here. But research in college is learning something new that no human ever knew before, and I'd encourage you to get involved in it as soon as you can. So thanks again for the opportunity to talk with you, and I'm sure the other speakers and I would be happy to answer any of your questions afterwards.